In this video, we're going to go ahead and cover section 10.6, Parametric Equations, part of Unit 10, Topics in Analytic Geometry. Before I go into the definition of a parametric equation in math language, um, what is this used for? Why do we need to know about it? So what we're going to do is talk about how to kind of combine two different functions based on x and y. So for example, f of x equals this, g of x equals that, based on x and y. And we combine them into this parametric equation that is a function of something that they both have in common, often time, or t for time. This is our third variable, and we do call it a parameter. An example of this would be maybe something that's orbiting in space, a star, the moon, something that's going on in space that is related to several factors. Say, and I'm not a science person, so I really can't be specific, but say something is based on off of the orbit of the sun and off of something else. But all of those factors are related to time, and so time can kind of combine them all into this one equation, which is our parametric equation. So let's go ahead and just, another application just to kind of, off the top of my head, is there is this thing called integer geometry, which actually relates right triangles with three different components. So it gets pretty cool later on. Like we're talking Cal 2, Cal 3. But anyway, let's go ahead and get right into this. So we have that parametric equations can be used to write x and y as functions of t. Again, that could be our time, often showing when an object is at a given point, and it's basically based on all the other factors that go into it. It also gives direction, which we're going to focus on in this particular unit. Um, the resulting path of this object, or whatever we're talking about, is what's called a plane curve. So what is a plane curve? If f and g, so we have these two functions, are continuous functions of some t between some intervals, so think of like a domain, okay, then the set of ordered pairs that go with these functions, f of t and g of t, is a plane curve, C. We call that C. By the way, these are italicized I's and C's. The following equations, x equals f of t and y equals g of t, are parametric equations for this plane curve, and t is our parameter. In other words, these two equations are both based off of my time. Okay, and they kind of combine into this one problem. So we're going to start with an example, and this one is given to us already just because, again, of the time. So we have that, I don't have my, here we go, my calculator here to cover the solution. We have, don't mind that, that was from last notes. Sketch describe the orientation of the curve given by x equals 2t and y equals 4t squared plus t, where t is between -2 and 2. So this is kind of like our domain, okay, our restriction. So how do we solve this? The solution, the easiest method I would say, is to kind of make a table, and you'll notice here for t, I actually used numbers between -2 and 2, and you can kind of, pick and choose. I chose easy ones. I chose integers because I don't want to deal with decimals right now, not for this. So what I do is I take my t values and I'm going to input them into x and into y. So these two equations are right here. If I plug in -2 into this, 2 times -2 is -4, 2 times -1 is -2, 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4. So that's where these values are coming from, just plugging in my t into this equation. We do the same thing for y, and I did kind of show the work on this one a little bit just so you can see a little bit better. So where my t is, I plugged in -2, we did 4 times -2 squared plus 2. That's going to be 4 times 4 is 16 plus 2 is 18. -1 squared is 1 times 4, 4 plus 2 is 6, and so forth. And what happens is we combine these numbers. Oh, my pen's giving out. Of course, it would do that right when I start the video. There we go. All right, so these numbers and then the numbers that came from this column, which are basically these ones, and we make an ordered pair, x, y, that is a function of t. So they depend on this variable t, okay? And I'm going to go ahead and plot those here on the side, we already did. And you will notice that we do have all our points. So -2, 18, -1, 6, 0, 2, and then 2, 18. And you'll also notice that I have these like little arrow looking things. This is what I was talking about, the direction of where this object, whatever it is that's moving, is moving along the curve. So it's going to the right, so to speak, in this motion, because this is where we started. So our first number coming from the left, -2, this is our starting point. And then the numbers just kind of increased that from that way. They went over to the right. So we're going to follow that path and end. And we do end here because, again, our restriction said that it's between -2 and 2. So there you go. This is the plane curve for these two parametric equations as a function of time, or t, whatever t represents. And I do have a little side note down here that we're going to use in the next example. So I thought it'd be kind of neat to include it here. It said if x equals 2t, then that means, in other words, my original x value, I'm not, sorry, x value, my original function, x equals 2t, then we can solve for t. We can say, well, let's divide both sides by 2, and that's going to give me x over 2 is equal to t. And then from there, I can actually plug this into y, because y is a function of t as well. So I can combine them. This is what I meant earlier when I was saying combining. Maybe I I hope it didn't confuse you there. But I'm going to combine these two by plugging in what t is equal to into y. So this was 4t squared plus 2. I'm going to plug it into t, not y. So there's x over 2 squared, which is the same as x squared over 4. The 4's just give me a 1, so you're left with y equals x squared plus 2, which is the same picture that I have up here, sort of, kind of, right? You have this is a parabola. This would be a parabola, right, with a center of center of 0, 2. I shouldn't say center, I'm sorry. Y-intercept is what I meant. Y-intercept of 0, 2. And yeah, you have the point, you have the curve going up like a normal parabola, but again, it is going to be restricted to this domain, or I guess in terms of x, you just put an x here instead. But just wanted to show you this because this little process is actually called eliminating one of the terms, and we're going to do that in the next example. So let's go ahead and jump over. Hopefully this video is not too long, because like I said, they're kind of different, yeah? So let's look at example 2. This one is eliminating the parameter, which is kind of what I did in the previous example on that side note. We eliminated um, the the parameter of t by rewriting it in terms of x, yeah, and then we just solved it that way. So here we're going to sketch the curve represented by these two equations by eliminating the parameter and adjusting the domain of the resulting rectangular equation. Now I did not mention this before, but a rectangular equation is what we're used to. So that y equals x squared plus 2 that we found on the previous page at the bottom, that's a rectangular equation. That's the normal stuff that we've already seen. Okay, so just so you know, these are parametric because they're based on time, or t, whatever t is, and rectangular is the normal stuff, what we're used to, relatively speaking. Okay. Okay, so how are we going to do this? We're going to do kind of what I did before, where we're going to solve one of these for either, for time, for t, so we can plug that into the other one, or vice versa. Here you get to choose. I'm going to choose this one just because I see that one has, more going on the top. So I'm going to solve for this one. I'm going to say x is equal to 1 over square root of t minus 1. And I'm going to solve for t. How am I going to do that? Well, I see that I do have a square root. So my first instinct is to square something. So I'm going to do that. I'm going to do x squared is equal to all of this squared. And what that's going to do for me is it's going to get rid of the root, because if I square 1, it's still equal to 1, right? This is x squared is equal to 1 over, but if I square this one, remember you square both of them, the root goes away. So now I just have t minus 1. And that just looks a little bit easier to work with. So from here, I am going to do kind of not a trick, but I want the t on the top, because on the bottom it just looks weird. So I'm going to put this over 1, and I'm going to flip everything. And you're allowed to do that. If you cross multiply, you get the same thing, and then you divide. So we're going to flip this. So if you want, you can write the word flip. If I flip this side 1 over x squared, then I could flip this side, which is going to be t minus 1 over 1, which of course is the same as just t minus 1 is equal to this, right? So 1 over x squared is equal to t minus 1. I just have to move the 1 over. So plus 1. So we have 1 over x squared plus 1 is equal to t. And this is still kind of messy because I kind of want just one fraction. So what I'm going to do is I'm going to change this 1 to x squared over x squared. So I end up with 1 over x squared plus x squared over x squared is equal to t, which I'm allowed to do because this is still equal to 1. And I'm doing this so that I can find a common denominator. Okay, so now that I have common denominators, I will have, and I'm going to write it as t equals now. So t equals to 1 plus x squared all over x squared. And I did all that. I know it's actually kind of messy. It's a little messier than I'm used to. After I did that, I can take this and plug it into the other equation. So that's what I'm going to do here. I'm going to plug in, I know I'm all over the place today. We're going to plug in to y. Okay, so y is equal to, that's up here, t plus 1 over t minus 1. So from here, I'm going to plug this whole expression that I found down here. So y equals, it was 1 plus x squared over x squared plus 1 all over 1 plus x squared over x squared minus 1. So I have this ugly fraction, but you know what? Fractions are sometimes fun to deal with because we get to use our math skills. Yeah, I'm going to do the same thing I did before where I'm going to change these 1's into x squared over x squares to make, so I can have the same denominator. Okay, so now we have, let's see, we're going to have 1 plus x squared over x squared plus x squared over x squared. And that is the top fraction, so that's this part right here. And on the bottom, I have 1 plus x squared over x squared minus x squared over x squared. And now I have common denominators, so I can combine everything on the top. So I can put all this together, and I can put all of this together. And just kind of looking ahead, you see that you have 2x squared, so it's going to be 1 plus 2x squared, again over my x squared here, all over. On this one, you have 1 plus x squared minus x squared, so you actually get rid of those. It's just going to give me 0, so I'm just left with 1 over x squared. And this is looking a little bit nicer now. You will notice that we do have a double fraction, so we're going to go ahead and do our keep flip change trick here and get rid of some more stuff. So this is the same as the top fraction, so 1 plus 2x squared, maybe some of you can see it already, times the reciprocal of this one, so x squared over 1, and check that out, they are gone, it's equal to 1. So that's super nice because that means that we just have this over 1, which is the same as 2x squared plus 1. I just wrote it, with the x squared first because, well, we like to put the x squared first. So this is equal, this is y. So now we have eliminated the parameter of t, and we have it in terms of x and y. So we can graph this, no problem. I believe that's what they wanted here. But before I do that, I do have to put a domain restriction. So for even though we did eliminate the t parameter, we still have here at the top that x is equal to all of this. And if you look, since we do have a fraction, we have to remember that we cannot divide by 0. That's a taboo, right? So we're going to have to let x be greater than whatever, or equal to whenever this is equal to 0. So in this case, it would be when x is equal to 1 or t is equal to 1. Because if I put a 1 here, you get 1 minus 1 is 0. So for our restriction down here, we do have to put, and I'm sorry, not equal to, just greater than. We have to define that. So for our domain restriction, x has to be greater than 0. Again, because if you want to kind of put this here in the notes, 1 over square root of t minus 1. If we were to put I'm sorry, not 0, what am I saying? 1. We plug in a 1 into this, we get 1 over square root of 1 minus 1, which is 1 over square root of 0, which is 1 over 0, which is not allowed. So we can't have that. So we do have to have this restriction. for our domain. Okay, so let's go ahead and graph this now really quickly. We're going to have our graph, and I know that 2x squared plus 1 is going to have its y-intercept and vertex actually at 0, 1, just from past knowledge. And I know that it kind of does this, something like that. But again, since I want it to be greater than 1, it's going to be just this side over here. Let's see, so about right here. Okay, something like that. Hopefully your picture is nicer than mine. Okay. And yeah, I believe that that is it. So we can finish that one. Next example, we have example number 3. Sketch the curve represented by each set of equations by eliminating the parameter. And then we have 2 examples. Notice for this one, we actually have some thetas. So we're going to use a little bit of trigonometry in this one. I'm going to work with A first. I'm going to try not to take up too much space because I only have this one page for this one. So I'm going to take these 2 equations, x equals 5 cosine of theta and y equals 3 sine of theta. And what I'm going to do, and don't forget we do have a restriction, so 0 less than theta less than or equal to 2 pi. For this one, we're going to use one of the identities. What I'm trying to do is combine these two somehow into one equation. And I do know that there's a Pythagorean identity that relates cosine and sine, namely sine squared theta plus cosine squared theta is equal to 1. So we're going to use that for this one. And for whenever you have angles, you tend to kind of want to use these. Okay, so just an FYI there. So let's go ahead. What we're going to do is we're going to solve both of these for um, cosine and sine. So because if we have cosine and sine, we can plug them into this right here. So for this one, we're going to have, let's see, I have to divide both sides by 5. So I get x over 5 is equal to cosine of theta. For this one, I'm going to divide both sides by 3. So I get y over 3 is equal to sine of theta. And now I can plug this and this into its corresponding place over here. So let's do that. We're going to have x over 5 squared plus y over 3 squared is equal to 1. And then from there, we're just going to square everything. So x squared over 25 plus y squared over 9 is equal to 1. And this is our equation. And we can see that this is an ellipse. Yay, conics, yeah? This is an ellipse. And because our 25 is bigger than 9, this tells me that it's going to be a horizontal ellipse at that, where A is equal to 5 and B is equal to 3. And we have a center of 0, 0. So I'm just going to put like that real quick, center of 0, 0. So we're going to go ahead and sketch that real quickly. Let's do that right underneath. We're going to have, let's see, we have 0, 0, and then we have horizontal. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there are 2 points, and then we have our minor axis of 3. So 1, 2, 3, 1, 2, 3. And here is my ellipse, and I'll put the direction in just a bit. For this one, we are going to put the direction. Since my restriction for this one was between 0 and 2 pi, remember this is where 0 starts. You can kind of think of it like a graph on a graph. Put the unit circle on here. So 0, pi halves, pi, 3 pi halves, and then 2 pi over here again. So we're going from 0 all the way to 2 pi. So that means we're going to go counterclockwise. And there you go. That is it for this one. Not bad, right? Not bad at all. Let's go ahead and try letter B. So for letter B, I have, again, I'm just gonna copy get this a little bit straight. I'm gonna copy the equation real quick. We have x is equal to -1 plus tangent of theta. And then we have y is equal to 2 plus 2 secant theta. And my restrictions are pi halves is less than theta is less than 3 pi halves. So just to kind of, so we know what this means right here, if you do your unit circle, we're looking at this part right here only. So we're going to look at whatever's on this side only because pi halves is here and 3 pi halves is over here. So that way we know how to draw the graph when we get there. I also noticed that I have tangent and secant for this one, and there is a Pythagorean identity that relates those two. I want to say it's 1 plus tangent square theta is equal to secant square theta, but I don't want it to look like that because I want it to probably equal to 1. If it's anything like the one before, it's going to be another conic, right? So I'm going to move the tangent theta to the other side, which gives me 1 is equal to secant square theta minus tangent square theta. And just because I see that there's a minus here, it's probably going to be a hyperbola, but you know what? Let's go through it and see, okay? So same thing, we're going to solve for tangent theta. I move the 1 to the other side, so I get x plus 1 is equal to tangent theta, and we're done with that one. For this one, I have to move the 2, so let's do that. So y minus 2 is equal to 2 secant theta, and then I have to divide both sides by 2, so divide everything by 2, which means that y minus 2 over 2 is equal to secant theta. So these are the two that I'm kind of going to work with, okay? Let's plug this and this into our equation. We have 1 equals, secant is all of this, so y minus 2 over 2 squared, because we have a square, minus x plus 1 squared. I'm going to square the top and the bottom, so I get 1 is equal to y minus 2 squared over 4. And I'm going to leave that one like that, but I'm going to put it over 1, just so I get that format of the hyperbola, which it turns out this is going to be. So this one is a hyperbola. And based on what I have here, I can see that the center is going to be -1 and 2, because even though the y is first, this just tells us that it's going to be vertical, right? So we should probably put that. It's going to be vertical. But it's still going to be -1, 2 for the center. So -1, comma 2, and then our a would be equal to the square root of that, which is 2. Our b is equal to 1. And I think that's all we need. So let's the page here. So we have our parabola, I'm sorry, not parabola, hyperbola at -1, 2. That is the center. Remember hyperbolas, you have the center is like the center between the two curves. So it's not the actual middle of the actual curve, but it's between the two curves of the transverse axis, so to speak. And then we have, let's see, the distance of A is 2. So from here, I'm going to go down 2. So there's one vertex. And then I'm going to go up 2. There's another vertex. And B gives me the conjugate axis, which is 1 over this way. I'm not going to put a point, but just kind of use it as a guide. And we can draw our little box here, a little rectangle. And then we can draw the asymptotes that go through it, because the asymptotes will give us a better idea of where our hyperbola is going to be sketched. So remember from this picture up here, okay, this picture up here, that we had pi halves up here and 3 pi halves down here. So I'm only going to want whatever's on the left side. So I'm going to go ahead and stop there, and then continue this side, stop here, and then continue this side. So it looks kind of weird, kind of like that. And for the direction, we did start with pi half, so going around the circle, going this way, we'll be going kind of like that. So that way, and then this way. So kind of a weird one, but it is what it is, right? And that's it. That is it for this one. Okay, let's go ahead and do one more. And this last one is worked out for us again because of the time. Hopefully I haven't gone too over so far. For this one, oh, look at my cool calculator. Let's just not distract you with that. We have find a set of parametric equations to represent the graph of y equals x squared plus 2 using each parameter. So for this one, we're actually going to be rewriting some of these by doing the following. We have these two equations, and I'm going to just kind of plug some stuff in. So let's look at letter A first. I'm going to plug in, since t is equal to x, that means that x equals t. So there's really not too much work to do for this one. But here's my equation, right? Here's my rectangular equation. And I'm going to plug in wherever I have an x, I just kind of put a parentheses. I'm going to put in what x is equal to, in this case, p. So t squared plus 2, and there it is, y equals t squared plus 2. I did go ahead and include the graph just for your information, but I do recommend you copy it down. For this one, to get the arrows and all that, what I did is I went ahead and used the first example that we did. I used that method where you kind of make a little table and you do your t variable here, and then you go ahead and plug in the values for x and y. So x is the same as t, so those are the same. And then for y, well, y is equal to t squared plus 2. That's what we found. So you just plug in those values, negative 2 squared plus 2, etc. And these are the points that we get. So with these points, I was able to construct my curve. And then since we are starting with this one, at least, well, we're not starting there, but with the points that I chose here, going left to right, negative 2, 6 is the first one, so it tells us that the arrows are going this way. Okay, I did the same thing for the second one. Now, the second one, the graph should be the same, but the orientation might be different and the direction might be different. Well, we'll see. This one has t is equal to 2 minus x, so we do have to solve for x first, which I did right here. I moved over my 2, and then since you have negative x, you just have to, if you divide all this by negative 1, you get the opposite. So negative t plus 2 is equal to x, or x equals 2 minus t. And I use this one just because I don't know, negative t looks kind of weird to me like that. So this is the one I plugged into this equation right here. So there you have it again. We have our y equals something squared plus 2. I plugged in the something, which is 2 minus t. This is a binomial, so we just expanded it. We FOILed all this, and we got 2 times 2 is 4, minus 2t plus t squared. Bring down the 2, combine like terms, and we end up with this right here. And actually, I went more steps. I combined the 2t's first, so I did these two first. And then I combined the 4 and the 2, which gave me 6, and I put it in order just because, well, it's a quadratic, and we wanted to look like a quadratic. So there's my equation. And you'll notice that for this one, and I kind of messed up a little, so you'll see that also. Oops, don't copy that. I did my table again down here. Let me get this a little bit closer because right now I went a little bit off the page. Here's my little table, just like the one I did before. But now with these values, you have your t, you have your x, you have what y is equal to, which is that quadratic up here. You plug in these numbers into x and into y, and these are the numbers that you get over here. Okay, so this is 4, 18, 2, 6, and then 0, 2. And if I graph these ones, well, it looks the same. The graph looks the same, but since we started with 418, so this point right here is 418, that is our starting point. And you'll notice that the orientation is backwards, it's opposite of the other one. Kind of cool, kind of weird. That's parametric. That's it, guys. If you have any questions, as always, please let me know. Thanks so much.